Hello Year 12 and welcome to our fourth video here for continuous probability density functions. We're looking at the standard normal distribution today. Now normal distribution in this case refers to something quite specific. We're talking about a normal or Gaussian distribution, and it has a graph that looks like this. Sometimes it's called a bell curve. I might have seen these sorts of things before. Normal distribution occurs naturally in many situations, and often in fairly complex situations. If I were to measure the height of every student in Year 12 in New South Wales, the distribution would look a little bit like this. Okay, now that wouldn't necessarily be a probability distribution, because I wouldn't be describing the probability, I'd be describing the height, and it certainly wouldn't have a mean, in this case, of 0, but nonetheless the shape of that curve would be similar, and we could modify it in some way. But nonetheless, this is called a normal distribution, or sometimes a Gaussian distribution. It's got a few important properties. It's symmetrical. Geez, that was fancy, look at that. Here it goes again. Right, symmetrical about the mean and also the median, right, same place. It has one global maximum, which occurs when x is equal to the mean, right? So there we go, that's my global maximum, just the one. And it has 2 points of inflection, right? Remember, that's where the second derivative is 0, it changes concavity, and these occur one standard deviation either side of the mean. So that's those 2 points there. You can see a change in concavity. If you look closely, you can see those 2 points of inflection. One standard deviation above the mean and one standard deviation below the mean. In its standard form, it has this this equation: 1 over square root of 2 pi multiplied by e to the negative half of x squared. Anyway, that's a reasonably complex function, and for that reason integrating it is a little bit of a problem, and therefore finding the area under the curve is not super easy. So what we're going to do here in this particular example, I'm going to use the trapezoidal rule to estimate the area under the curve, which tells me the probability, right? So here's my standard form of the function, and I want to find the probability that x is between 0 and 1, right? That is, I want to find the area between that curve and the x-axis between over the domain 0 to 1. I'm going to use trapezoidal rule. I'm going to use 2 applications of it, which means that I need 3 values. And I have to calculate the value of the function at the lower bound, 0, at the upper bound, 1, and halfway in between. Right, that gives me 2 strips. So 3 values of x, and I need to find the relevant function values of those, right? So the function of 0, substitute 0 into that, and I find it is approximately 0.39894. You'll notice I'm not using exact values here because, look, it's only an approximation. So a good number of decimal places is just fine. At 0.5, substitute that in, and 1. I'm after an answer correct to 2 decimal places, and I'm carrying out a few extras there. So, using the trapezoidal rule, I get this expression here. Let's just go over those things. So, my trapezoidal rule begins with the width of the entire interval. Right, so that's from 1 to 0. the total width of that is 1 unit, 1 minus 0, and I divide that by 2n, or twice times the number of applications, or the number of strips. So 2 strips here from 0 to 0.5 and 0.5 to 1. So that's 1 minus 0 over 2 times 2. Then I have the first function value and the last function value, and 2 of all of the other function values in the middle. Only have 1 in the middle in this case, so twice that one there. And that's because this function value is essentially one of the sides. Well, it's the right-hand side of my first trapezium, and it's the left-hand side of my second trapezium. So that's why it gets used twice, it's double. I evaluate that, and it's approximately 0.336261. I was asked for 2 decimal places, so approximately 0.34. That's using the trapezoidal rule to estimate probabilities. That's one of the ways I could perhaps do this, and I wouldn't choose that method unless you were specifically directed to. One of the other ways that we're asked to do this sometimes is because it's quite a standard function that we have a table of values already calculated for us. It might look a bit like this. And what this does is it calculates the area between the curve, the function, and the x-axis from negative infinity up to some value here, right? Which describes how many standard deviations I am above the mean. The left-hand column represents the first, the first 2 digits, I guess, the unit and the tenths, and the columns represent, in this case, the hundredths of standard deviations above the mean. And of course here at 0 standard deviations above the mean, I'm at the mean, and from negative infinity to the mean, I have half of that total area enclosed, 0.5. If I go 0.01 standard deviations above the mean, it's a little bit more than half of the total area under that curve. So it's 0.5040, and so on. If I go up to, right, this table's only going to 1.49 standard deviations, but you can see that's encompassing about 93% of the area under the curve already. So sometimes we use a table of results. Now, there is this other method called an empirical rule, which is essentially a simplified version of that table. Right, a simplified version of that table. And it applies for whole values of standard only for full standard deviations either side of the mean. So I get this looking curve here. That's my normal distribution curve, and that's on your reference sheet. But not all of these numbers are written on the reference sheet. My empirical rule tells me that 60% of all values, or 60% of the total area under that curve, lie between 1 standard deviation either side of the mean. Now, because of the symmetry, that means that if I just go 1 standard deviation above, it's half of that 68 is 34%. And if your memory holds, then you might remember that that's pretty close to the answer that we calculated using the trapezoidal rule from 0 to 1. So 68% 1 standard deviation either side means 34%. If I just go from 0 to 1 or negative 1 to 0. The second part of my empirical rule is 95% of all values lie from 2 standard deviations below to 2 standard deviations above. Now that would mean that half of that, which is 47.5% of all values lie between 0 and 2 standard deviations. And knowing that 0 to 1 is 34 means that from 1 to 2, right, that little area there is just 13.5% of the area. Finally, the third part of my empirical rule, there are these 3 parts to it, is that 99.7% of all values lie from -3 standard deviations below to 3 standard deviations above the mean. And doing these fairly simple calculations, I find that, for example, from 2 standard deviations above to 3 standard deviations above, that little part there of my area is 2.35% of the total area. Righto, that's the empirical rule. So we did 3 things here with the normal distribution. We looked at using the trapezoidal rule. We looked at using a table of values, if only briefly, and the empirical rule. We learnt generally about a normal or Gaussian distribution, about its symmetry, the mean and the median, the 2 points of inflection. Righto, that's it. Any questions? Let me know. Otherwise, I will see you in class. Coming up next are general normal distributions. Sounds like someone in the army. Never mind. General normal distributions, and I'm going to refer you to my videos there for Standard 2, because it's where we start to overlap with their work. Anyway, see you in class. Hope it helps.